By now, you've seen a lot of different learning algorithms, and if you've been following along these videos, you should consider yourself an expert on many state-of-the-art machine learning techniques. But even among people that know a certain learning algorithm, there's often a huge difference between someone that really knows how to powerfully and effectively apply that algorithm versus someone that's less familiar with some of the material that I'm about to teach and who doesn't really understand how to apply these algorithms and can end up wasting a lot of their time trying things out that don't really make sense. What I'd like to do is make sure that if you're developing a machine learning system, that you know how to choose what are the most promising avenues to spend your time pursuing. And in this and the next few videos, I'm going to give a number of practical suggestions, advice, guidelines on how to do that. And concretely, what I'm going to focus on is the problem of, suppose you're developing a machine learning system or trying to improve the performance of a machine learning system. How do you go about deciding what are the promising avenues to try next? To explain this, let's continue using our example of learning to predict housing prices. And let's say you've implemented regularized linear regression, thus minimizing that cost function j. But suppose that after you take your learned parameters, if you test your hypothesis on a new set of houses, suppose you find that it's making huge errors in its prediction of the housing prices. The question is, what should you then try next in order to improve the learning algorithm? There are many things that one can think of that could improve the performance of your learning algorithm. One thing that you could try is to get more training examples, and concretely you can imagine maybe setting up phone surveys, going door to door to try to get more data on how much different houses sold for. And the sad thing is, I've seen a lot of people spend a lot of time collecting more training examples, thinking, oh, if we have twice as much or 10 times as much training data, that's certainly got to help, right? But sometimes getting more training data doesn't actually help, and in the next few videos we'll see why, and we'll see how you can avoid spending a lot of time collecting more training data in settings where it's just not going to help. Other things you might try are to, well, maybe try a smaller set of features. So if you have some set of features, x1, x2, x3, and so on, maybe a large number of features, maybe you want to spend time carefully selecting some small subset of them to prevent overfitting. Or maybe you need to get additional features. Maybe the current set of features aren't informative enough, and we want to collect more data in the sense of getting more features. And once again, this is a sort of project that can scale up to be huge projects. You can imagine, again, phone surveys to find out more about houses, or extra land surveys to find out more about the pieces of land, and so on. So a huge project. And once again, it would be nice to know in advance if this is going to help before we spend a lot of time doing something like this. We can also try adding polynomial features, things like x1 squared, x2 squared, and product features x1, x2. You can spend quite a lot of time thinking about that. And we can also try other things like decreasing lambda, the regularization parameter, or increasing lambda. Given a menu of options like these, some of which can easily scale up to like maybe 6-month or longer projects, unfortunately, the most common method that people use to pick one of these is to go by gut feeling, in which what many people will do is sort of randomly pick one of these options. Like maybe say, oh, let's go and get more training data, and easily spend 6 months collecting more training data. Or maybe someone else will randomly say, well, let's go collect a lot more features on these houses in our data set. And I have a lot of times, sadly, seen people spend literally 6 months doing one of these avenues that they had picked sort of at random, only to discover 6 months later that that really wasn't a promising avenue to pursue. Fortunately, there's a pretty simple technique that can let you fairly quickly rule out half of the things on this list as being potentially promising things to pursue. And it's a fairly simple technique that if you run, can easily rule out many of these options and potentially save you a lot of time pursuing something that's just not going to work. In the next 2 videos after this, I'm going to first talk about how to evaluate learning algorithms, and in the next few videos after that, I'm going to talk about these techniques, which are called machine learning diagnostics. And what a diagnostic is a test they can run to get insight into what is and what isn't working with an algorithm, and which will often give you insight as to what are promising things to try to improve a learning algorithm's performance. We'll talk about specific diagnostics later in this video sequence, but I should mention in advance that diagnostics can take time to implement. It can sometimes take quite a lot of time to implement and understand, but doing so can be a very good use of your time when you're developing learning algorithms, because they can often save you from spending many months pursuing an avenue that you could have found out much earlier just was not going to be fruitful. So in the next few videos, I'm going to first talk about how to evaluate your learning algorithms, and after that I'm going to talk about some of these diagnostics which will hopefully let you much more effectively select what are useful things to try next in order, if your goal is to improve the performance of your machine learning system. In this video, I'd like to talk about how to evaluate a hypothesis that has been learned by your algorithm. In later videos, we'll build on this to talk about how to prevent the problems of overfitting and underfitting as well. When we fit the parameters of our learning algorithm, we think about choosing the parameters to minimize the training error. One might think that getting a really low value of training error might be a good thing, but we've already seen that just because a hypothesis has low training error, that doesn't mean it's necessarily a good hypothesis, and we've already seen the example of how a hypothesis can overfit and therefore fail to generalize to new examples that are not in the training set. So how do you tell if a hypothesis might be overfitting? In this simple example, we could plot the hypothesis h of x and just see what was going on. But in general, for problems with more features than just one feature, for problems with a large number of features like these, it becomes hard or maybe impossible to plot what the hypothesis function looks like, and so we need some other way to evaluate our hypotheses. The standard way to evaluate a learned hypothesis is as follows. Suppose we have a data set like this. Here I've just shown 10 training examples, but of course usually we may have dozens or hundreds or maybe thousands of training examples. In order to make sure we can evaluate our hypothesis, what we're going to do is split the data we have into two portions. The first portion is going to be our usual training set, and the second portion is going to be our test set. And a pretty typical split of all the data we have into a training set and test set might be around, say, a 70% 30% split, with more of the data going to the training set and relatively less to the test set. And so now, if we have some data set, we might assign only, say, 70% of the data to be our training set, where here M is, as usual, our number of training examples, and the remainder of our data might then be assigned to become our test set. And here I'm going to use the notation M subscript test to denote the number of test examples. And so in general, this subscript test is going to denote examples that come from my test set, so that x1 subscript test, comma y1 subscript test is my first test example, which I guess in this example might be this example over here. Finally, one last detail, whereas here I've drawn this as though the first 70% goes to the training set and the last 30% to the test set, if there is any sorted ordering to the data, it'd actually be better to send a random 70% of your data to the training set and a random 30% of your data to the test set. So if your data were already randomly sorted, you could just take the first 70% and last 30%, but if your data were not randomly ordered, it'd be better to randomly shuffle or to randomly reorder the examples in your training set before sending the first 70% to the training set and the last 30% to the test set. Here then is a fairly typical procedure for how you would train and test a learning algorithm, maybe linear regression. First, you learn the parameters theta from the training set. So you minimize the usual training error objective J of theta, where J of theta here was defined using that 70% of all the data you have. There's only the training data. And then you would compute the test error. And I'm going to denote the test error as J subscript test. And so what you do is you take your parameter theta that you've learned from the training set and plug it in here and compute your test set error, which I'm going to write as follows. So this is basically the average squared error as measured on your test set. It's pretty much what you'd expect. So run every test example through your hypothesis with parameter theta and just measure the squared error that your hypothesis has on your m subscript test examples. And of course, this is the definition of the test set error if we are using linear regression and using this squared error metric. How about if we were doing a classification problem and say using logistic regression instead? In that case, the procedure for training and testing, say logistic regression, is pretty similar. First, we will learn the parameters from the training data, that first 70% of the data, and then we will compute the test error as follows. It's the same objective function as we always use for logistic regression, except that now it's defined using our m subscript test examples. While this definition of the test set error j subscript test is perfectly reasonable, sometimes there's an alternative test set metric that might be easier to interpret, and that's the misclassification error. It's also called the 0-1 misclassification error, with 0-1 denoting that you either get an example right or you get an example wrong. Here's what I mean. Let me define the error of a prediction, that is h of x, and given a label y as equal to 1 if my hypothesis outputs a value greater than or equal to 5 and y is equal to 0, or if my hypothesis outputs a value less than 0.5 and y is equal to 1. Right? So both of these cases basically correspond to if your hypothesis mislabeled the example, assuming you thresholded at 0.5. So either thought it was more likely to be 1, but it was actually 0, or your hypothesis thought it was more likely to be 0, but the label was actually 1. And otherwise, we define this error function to be 0 if your hypothesis basically classified the example y correctly. We could then define the test error using the misclassification error metric to be 1 over m test of sum from I equals 1 to m subscript test of the error of h of xi test, comma yi. And so that's just my way of writing out that this is exactly the fraction of the examples in my test set that my hypothesis has mislabeled. And so that's the definition of the test set error using the misclassification error or the 0-1 misclassification error metric. So that's the standard technique for evaluating how good a learned hypothesis is. In the next video, we'll adapt these ideas to helping us do things like choose what features, like degree of polynomial, to use with a learning algorithm, or choose the regularization parameter for a learning algorithm. Suppose you'd like to decide what degree of polynomial to fit to a dataset, so that what features to include to give to your learning algorithm. Or suppose you'd like to choose the regularization parameter lambda for a learning algorithm. How do you do that? These are called model selection problems, and in our discussion of how to do this, we'll talk about not just how to split your data into a train and test sets, but how to split your data into what we'll discover is called the train, validation, and test sets. We'll see in this video just what these things are and how to use them to do model selection. We've already seen a lot of times the problem of overfitting, in which just because the learning algorithm fits a training set well, that doesn't mean it's a good hypothesis. More generally, this is why the training set error is not a good predictor for how well the hypothesis will do on new examples. Concretely, if you fit some set of parameters, theta 0, theta 1, theta 2, and so on, to your training set, then the fact that your hypothesis does well on the training set, well, this doesn't mean much in terms of predicting how well your hypothesis will generalize to new examples not seen in the training set. And the more general principle is that once your parameters were fit to some set of data, maybe the training set, maybe something else, then the error of your hypothesis as measured on that same data set, such as the training error, that's unlikely to be a good estimate of your actual generalization error, that is, of how well the hypothesis will generalize to new examples. Now let's consider the model selection problem. Let's say you're trying to choose what degree polynomial to fit to data. So you choose a linear function, a quadratic function, a cubic function, all the way up to a 10th order polynomial. So it's as if there's one extra parameter in this algorithm, which I'm going to denote D, which is what degree of polynomial do you want to pick. So it's as if, in addition to the theta parameters, it's as if there's one more parameter D that you're trying to determine using your data set. So the first option is D equals 1. If you fit a linear function, we can choose D equals 2, D equals 3, all the way up to D equals 10. So we'd like to fit this extra sort of parameter, which I'm denoting by D. And concretely, let's say that you want to choose a model, that is, choose a degree of polynomial, choose one of these 10 models, and fit that model and also get some estimate of how well your fitted hypothesis will generalize to new examples. Here's one thing you could do. You could first take your first model and minimize the training error, and this would give you some parameter vector theta. And you could then take your second model, the quadratic function, and fit that to your training set, and this will give you some other parameter vector theta. In order to distinguish between these different parameter vectors, I'm going to use a superscript 1, superscript 2 there, where theta superscript 1 just means the parameters I get by fitting this model to my training data, and theta superscript 2 just means the parameters I get by fitting this quadratic function to my training data, and so on. And by fitting a cubic model, I get parameters theta 3 up to, say theta 10. And one thing we could do is then take these parameters and look at the test set error. So I can compute on my test set j test of 1, j test of theta 2, and so on, j test of theta 3, and so on. So I'm going to take each of my hypotheses with the corresponding parameters and just measure their performance on the test set. Now, one thing I could do then is, in order to select one of these models, I could then see which model has the lowest test set error. And let's just say for this example that I ended up choosing the 5th order polynomial. So this seems reasonable so far. But now let's say I want to take my fit hypothesis, this 5th order model, and let's say I want to ask, how well does this model generalize? One thing I could do is look at how well my 5th order polynomial hypothesis had done on my test set. But the problem is, this will not be a fair estimate of how well my hypothesis generalizes. And the reason is, what we've done is we've fit this extra parameter D, that is this degree of polynomial, and we fit that parameter D using the test set. Namely, we chose the value of D that gave us the best possible performance on the test set. And so the performance of my parameter vector theta 5 on the test set, that's likely to be an overly optimistic estimate of generalization error. Right? So that because I have fit this parameter D to my test set, it is no longer fair to evaluate my hypothesis on this test set. It's because I've fit my parameters to the test set, I've chosen the degree D of polynomial using the test set, and so my hypothesis is likely to do better on this test set than it would on new examples that it hasn't seen before, and which is what I really care about. So just to reiterate, on the previous slide, we saw that if we fit some set of parameters, say theta 0, theta 1, and so on, to some training set, then the performance of the fitted model on the training set is not predictive of how well the hypothesis will generalize to new examples. It's because these parameters were fit to the training set, so they're likely to do well on the training set even if the parameters don't do well on other examples. And in the procedure I just described on this slide, we just did the same thing. And specifically what we did was we fit this parameter D to the test set, and by having fit the parameter to the test set, this means that the performance of the hypothesis on that test set may not be a fair estimate of how well the hypothesis is likely to do on examples we haven't seen before. To address this problem, in a model selection setting, if we want to evaluate a hypothesis, this is what we usually do instead. Given a data set, instead of just splitting it into a train and test set, what we're going to do is instead split it into 3 pieces. And the first piece is going to be called the training set as usual. So let me call this first part the training set. And the second piece of this data I'm going to call the cross-validation set. Cross-validation. And I'm going to abbreviate cross-validation as CV. Sometimes it's also called the validation set instead of cross-validation set. And then the last part I'm going to call my usual test set. And a pretty typical ratio in which to split these things would be to send 60% of your data to your training set, maybe 20% to your cross-validation set, and 20% to your test set. And these numbers can vary a little bit, but this sort of ratio would be pretty typical. And so our training sets will now be only maybe 60% of the data, and our cross-validation set, or our validation set, will have some number of examples. I'm going to denote that M subscript CV, so that's the number of cross-validation examples. Following our earlier notational convention, I'm going to use XI CV, comma, YI CV to denote the I cross-validation example. And finally, we also have a test set over here with M subscript test being the number of test examples. So now that we've defined the training, validation, or cross-validation and test sets, we can also define the training error, cross-validation error, and test error. So here's my training error, and I'm just writing this as J subscript train of theta. This is pretty much the same thing. It's usually the same thing as the J of theta that we've been writing so far. It's just a training set error, as measured on your training set. And then J subscript CV is my cross-validation error. It's pretty much what you'd expect, just like the training error, except measured on the cross-validation data set. And here's my test set error, same as before. So when faced with a model selection problem like this, what we're going to do is, instead of using the test set to select the model, we're instead going to use the validation set or the cross-validation set to select the model. Concretely, we're going to first take our first hypothesis, take this first model, and say minimize the cost function, and this will give me some parameter vector theta for the linear model. And as before, I'm going to put a superscript 1 just to denote that this is the parameter for the linear model. We do the same thing for the quadratic model, get some parameter vector theta 2, get some parameter vector theta 3, and so on down to, say, the 10th order polynomial. And what I'm going to do is, instead of testing these hypotheses on the test set, I'm instead going to test them on the cross-validation set. I'm going to measure J subscript CV to see how well each of these hypotheses do on my cross-validation set. And then I'm going to pick the hypothesis with the lowest cross-validation error. So for this example, let's say, for the sake of argument, that it was my 4th order polynomial that had the lowest cross-validation error. So in that case, I'm going to pick this 4th order polynomial model. And finally, what this means is that that parameter d, remember d was the degree of polynomial, right? So d equals 2, d equals 3, up to d equals 10. What we've done is we've fit that parameter d, and we've set d equals 4, and we did so using the cross-validation set. And so this degree of polynomial, so the parameter, is no longer fit to the test set, and so we've now saved away the test set, and we can use the test set to measure or to estimate the generalization error of the model that was selected by this algorithm. So that was model selection and how you can take your data, split it into a train, validation, and test set, and use your cross-validation data to select a model and evaluate it on the test set. One final note, I should say that in the machine learning as it is practiced today, there are many people that will do that earlier thing that I talked about and said that isn't such a good idea of selecting your model using the test set and then using the same test set to report the error as though selecting your degree of polynomial on the test set and then reporting the error on the test set as though that were a good estimate of generalization error. That sort of practice, unfortunately, many people do it. If you have a massive test set, it's maybe not a terrible thing to do, but many practitioners, most practitioners of machine learning tend to advise against that, and it's considered better practice to have separate train, validation, and test sets. But I just warn you that sometimes people do, use the same data for the purpose of the validation set and for the purpose of the test set. So you only have a training set and a test set. And that's considered less good practice, but you will see some people do it. But if possible, I would recommend against doing that. If you run a learning algorithm and it doesn't do as well as you were hoping, almost all the time it will be because you have either a high bias problem or a high variance problem. In other words, either an underfitting problem or an overfitting problem. And in this case, it's very important to figure out which of these two problems, is it bias or variance or a bit of both, that you actually have. Because knowing which of these two things is happening will give a very strong indicator for what are the useful and promising ways to try to improve your algorithm. In this video, I'd like to delve more deeply into this bias and variance issue and understand them better, as well as figure out how to look at the learning algorithm and evaluate or diagnose whether we might have a bias problem or a variance problem, since this will be critical to figuring out how to improve the performance of a learning algorithm that you may implement. So you've already seen this figure a few times, where if you fit two simple hypotheses, like a straight line that underfits the data, if you fit a too complex hypothesis, then that might fit the training set perfectly, but overfit the data, and is maybe hypothesis of some intermediate level of complexity, so of some maybe degree 2 polynomial, so not too low and not too high degree, that's just right and gives you the best generalization error out of these options. Now that we're armed with the notion of training and validation in test sets, we can understand the concepts of bias and variance a little bit better. Concretely, let's let our training error and cross-validation error be defined as in the previous videos. Just say the squared error, the average squared error as measured on the training set or as measured on the cross-validation set. Now let's plot the following figure. On the horizontal axis, I'm going to plot the degree of polynomial. So as I go to the right, I'm going to be fitting higher and higher order polynomials. So way on the left of this figure, where maybe d equals 1, I'm going to be fitting very simple functions, whereas way here on the right of the horizontal axis, I have much larger values of d, so I have a much higher degree polynomial. And so here, that's going to correspond to fitting much more complex functions to your training set. Let's look at the training error and the cross-validation error and plot them on this figure. Let's start with the training error. As we increase the degree of the polynomial, we're going to be able to fit our training set better and better. And so if d equals 1, we're going to have a relatively high training error. If we have a very high degree polynomial, our training error is going to be really low, maybe even 0, because we'll fit the training set really well. And so as we increase the degree of polynomial, we find typically that the training error decreases. So I'm going to write j subscript train of theta there, because our training error tends to decrease with the degree of the polynomial that we fit to the data. Next, let's look at the cross-validation error. Or for that matter, if we look at the test set error, we'll get a pretty similar result as if we were to plot the cross-validation error. So we know that if d equals 1, we're fitting a very simple function, and so we may be underfitting the training set, and so we're going to have a very high cross-validation error. If we fit, an intermediate degree polynomial, we had a d equals 2 in our example in the previous slide, we're going to have a much lower cross-validation error because we're just fitting, finding a much better fit to the data. And conversely, if d were too high, so if d took on, say, a value of 4, then we're again overfitting, and so we end up with a high value for cross-validation error. So if you were to vary this smoothly and plot a curve, you might end up with a curve like that, where that's jcv of theta. And again, if you plot j test of theta, you get something very similar. And so this sort of plot also helps us to better understand the notions of bias and variance. Concretely, suppose you've applied a learning algorithm and it's not performing as well as you were hoping. So if your cross-validation set error or your test set error is high, how can we figure out if the learning algorithm is suffering from high bias or if it's suffering from high variance? So the setting of the cross-validation error being high corresponds to either this regime or this regime. So this regime on the left corresponds to a high bias problem. That is, if you're fitting a overly low order polynomial, such as a d equals 1, when we really needed a higher order polynomial to fit the data. Whereas in contrast, this regime corresponds to a high variance problem. That is, if d, the degree of polynomial, was too large for the data set that we have. And this figure gives us a clue for how to distinguish between these two cases. Concretely, for the high bias case, that is the case of underfitting, what we find is that both the cross-validation error and the training error are going to be high. So if your algorithm is suffering from a bias problem, the training set error will be high, and you might find that the cross-validation error will also be high. It might be a close, maybe just slightly higher than a training error. And so if you see this combination, that's a sign that your algorithm may be suffering from high bias. In contrast, if your algorithm is suffering from high variance, then if you look here, we'll notice that JTrain, that is the training error, is going to be low. That is, you're fitting the training set very well, whereas your cross-validation error, assuming that this is, say, the squared error, which you're trying to minimize, say, whereas in contrast, your error on the cross-validation set, or your cost function on the cross-validation set, will be much bigger than your training set error. So there's a double greater than sign. That's the math symbol for much greater than, denoted by two greater than signs. And so if you see this combination of values, then that might give you, that's a clue that your learning algorithm may be suffering from high variance and might be overfitting. And the key that distinguishes these two cases is if you have a high bias problem, your training set error will also be high. Your hypothesis is just not fitting the training set well. And if you have a high variance problem, your training set error will usually be low. That is much lower than your cross-validation error. So hopefully that gives you a somewhat better understanding of the two problems of bias and variance. I still have a lot more to say about bias and variance in the next few videos, but what we'll see later is that by diagnosing whether a learning algorithm may be suffering from high bias or high variance, I'll show you even more details on how to do that in later videos. But we'll see that by figuring out whether a learning algorithm may be suffering from high bias or high variance, or a combination of both, that would give us much better guidance for what might be promising things to try in order to improve the performance of a learning algorithm. You've seen how regularization can help prevent overfitting, but how does it affect the bias and variance of a learning algorithm? In this video, I'd like to go deeper into the issue of bias and variance and talk about how it interacts with and is affected by the regularization of your learning algorithm. Suppose we're fitting a high-order polynomial like that shown here, but to prevent overfitting, we're going to use regularization like that shown here. So we have this regularization term to try to keep the values of the parameters small. And as usual, the regularization sums from j equals 1 to m rather than j equals 0 to m. Let's consider three cases. The first is a case of a very large value of the regularization parameter lambda, such as if lambda were equal to 10,000, some huge value. In this case, all of these parameters, theta 1, theta 2, theta 3, and so on, will be heavily penalized, and so we'll end up with most of these parameter values being close to 0, and the hypothesis will be roughly h of x just equal or approximately equal to theta 0. And so we end up with a hypothesis that more or less looks like that. So it's more or less a flat, constant straight line. And so this hypothesis has high bias and it badly underfits this data set. So the horizontal straight line is just not a very good model for this data set. At the other extreme is if we have a very small value of lambda, such as if lambda were equal to 0. In that case, given that we're fitting a high-order polynomial, this is our usual overfitting setting. In that case, given that we're fitting a high-order polynomial basically without regularization or with very minimal regularization, we end up with our usual high variance overfitting setting. It's basically if lambda is equal to 0, we're just fitting it without regularization, so that overfits the hypothesis. And it's only if we have some intermediate value of lambda that is neither too large nor too small that we end up with parameters theta that give us a reasonable fit to this data. So how can we automatically choose a good value for the regularization parameter lambda? Just to reiterate, here is our model, and here is our learning algorithm's objective. For the setting where we're using regularization, let me define J train of theta to be something different, to be the optimization objective but without the regularization term. Previously, in an earlier video when we were not using regularization, I defined J train of theta to be the same as J of theta as a cost function. But when we're using regularization, when this is extra lambda term, we're going to define J train, my training set error, to be just my sum of squared errors on the training set, or my average squared error on the training set, without taking into account that regularization term. And similarly, I'm then also going to define the cross-validation set error and the test set error as before to be the average sum of squared errors on the cross-validation and the test sets. So just to summarize, my definitions of JTrain, JCV, and JTest are just the average squared error, or 1/2 of the average squared error on my training, validation, and test sets without the extra regularization term. So this is how we can automatically choose the regularization parameter lambda. What I usually do is maybe have some range of values of lambda I want to try out. So I might be considering not using regularization, or here are a few values I might try. I might be considering lambda equals 0.01, 0.02, 0.04, and so on. And I usually step these up in multiples of 2 until some maybe larger value. If I were doing this in multiples of 2, I actually end up with 10.24 instead of 10 exactly. But this is close enough, and the third and fourth decimal places won't affect your result that much. So this gives me maybe 12 different models that I'm trying to select amongst, corresponding to 12 different values of the regularization parameter lambda. And of course, you can also go to values less than 0.01 or values larger than 10, but I've just truncated it here for convenience. Given each of these 12 models, what we can do is then the following. We can take this first model with lambda equals 0 and minimize my cost function j of theta, and this would give me some parameter vector theta. And similar to the earlier video, let me just denote this as theta superscript 1. And then I can take my second model with lambda set to 0.01 and minimize my cost function, now using lambda equals 0.01 of course, to get some different parameter vector theta, and let me denote that theta 2. And for that I end up with theta 3, so if this is for my third model, and so on until for my final model with lambda set to 10, when or 10 or 10.24, I end up with this theta 12. Next, I can take all of these hypotheses, or all of these parameters, and use my cross-validation set to evaluate them. So I can look at my first model, my second model, fit with these different values of the regularization parameter, and evaluate them on my cross-validation set, and basically measure the average squared error of each of these parameter vectors theta on my cross-validation set. And I would then pick whichever one of these 12 models gives me the lowest error on the cross-validation set. And let's say, for the sake of this example, that I end up picking theta 5, the fifth order polynomial, because that has the lowest cross-validation error. Having done that, finally what I would do if I want to report a test set error is to take the parameter theta 5 that I've selected and look at how well it does on my test set. And once again, here is as if we fit this parameter theta to my cross-validation set, which is why I'm setting aside a separate test set that I'm going to use to get a better estimate of how well my parameter vector theta will generalize to previously unseen examples. So that's model selection applied to selecting the regularization parameter lambda. The last thing I'd like to do in this video is get a better understanding of how cross-validation and training error vary as we vary the regularization parameter lambda. And so just a reminder, right, that was our original cost function j of theta, but for this purpose we're going to define training error without using the regularization parameter and cross-validation error without using the regularization parameter. And what I'd like to do is plot this J-train and plot this J-CV, meaning just how well does my hypothesis do on the training set, and how well does my hypothesis do on the cross-validation set as I vary my regularization parameter lambda. So as we saw earlier, if lambda is small, then we're not using much regularization, and we run a larger risk of overfitting. Whereas if lambda is large, that is if we were on the right part of this horizontal axis, then with a large value of lambda, we run a higher risk of having a bias problem. So if you plot J-train and J-CV, what you find is that for small values of lambda, you can fit the training set relatively well because you're not regularizing. So for small values of lambda, the regularization term basically goes away and you're just minimizing pretty much the squared error. So when lambda is small, you end up with a small value for J-train. Whereas if lambda is large, then you have a high bias problem and you might not fit your training set well, so you end up with a value up there. So J-train of theta will tend to increase when lambda increases, because a large value of lambda corresponds to high bias, where you might not even fit your training set well, whereas a small value of lambda corresponds to if you can freely fit a very high degree polynomial to your data, let's say. As for the cross-validation error, we end up with a figure like this, where over here on the right, if we have a large value of lambda, we may end up underfitting, and so this is the bias regime, whereas and so the cross-validation error will be high. Let me just label that, so that's JCV of theta, because with high bias we won't be doing well on the cross-validation set. Whereas here on the left, this is the high variance regime, where if we have too small a value of lambda, then we may be overfitting the data, and so if we're overfitting the data, then the cross-validation error will also be high. And so this is what the cross-validation error and what the training error may look like on a training set as we vary the regularization parameter lambda. And so once again, it will often be some intermediate value of lambda that is sort of quote just right, or that works best in terms of having a small cross-validation error or a small test set error. And whereas the curves I've drawn here are somewhat cartoonish and somewhat idealized, so on a real data set, the curves you get may end up looking a little bit more messy and just a little bit more noisy than this. For some data sets, you will really see these broad sorts of trends, and by looking at the plot of the holdout cross-validation error, you can either manually or automatically try to select a point that minimizes the cross-validation error and select the value of lambda corresponding to low cross-validation error. When I'm trying to pick the regularization parameter lambda for a learning algorithm, often I find that plotting a figure like this one shown here helps me understand better what's going on and helps me verify that I am indeed picking a good value for the regularization parameter lambda. So hopefully that gives you more insight into regularization and its effects on the bias and variance of a learning algorithm. By now you've seen bias and variance from a lot of different perspectives. And what I'd like to do in the next video is take a lot of the insights that we've gone through and build on them to put together a diagnostic that's called learning curves, which is a tool that I often use to try to diagnose if a learning algorithm may be suffering from a bias problem or a variance problem or a little bit of both. In this video, I'd like to tell you about learning curves. Learning curves is often a very useful thing to plot if either you want to sanity check that your algorithm is working correctly or if you want to improve the performance of the algorithm. And learning curves is a tool that I actually use very often to try to diagnose if a particular learning algorithm may be suffering from a bias or a variance problem or a bit of both. Here's what a learning curve is. To plot a learning curve, what I usually do is plot JTrain, which is the, say, average squared error on my training set, or JCV, which is the average squared error on my cross-validation set. And I'm going to plot that as a function of m, that is, as a function of the number of training examples I have. And so m is usually a constant, like maybe I just have 100 training examples. But what I'm going to do is artificially reduce my training set size, so that deliberately limit myself to using only say 10 or 20 or 30 or 40 training examples, and plot what the training error is and what the cross-validation error is for these smaller training set sizes. So let's see what these plots might look like. Suppose I have only one training example, like that shown in this first example here, and let's say I'm fitting a quadratic function. Well, if I have only one training example, I'm going to be able to fit it perfectly, right? If fit a quadratic function, I'm going to have zero error on my one training example. If I have two training examples, well, with a quadratic function, I can also fit that very well. So even if I'm using regularization, I can probably fit this quite well. And if I'm using no regularization, I'm going to fit this perfectly. And if I have three training examples, again, I can fit a quadratic function perfectly. So if m equals 1, or m equals 2, or m equals 3, my training error on my training set is going to be 0, assuming I'm not using regularization, or it may be slightly larger than 0 if I am using regularization. And by the way, if I have a large training set and I'm artificially restricting the size of my training set in order to plot JTrain, here, if I set m equals 3, say, and I train on only 3 examples, then for this figure, I'm going to measure my training error only on the 3 examples that I actually fit my data to. And so even if I have, say, 100 training examples, but if I want to plot what my training error is for m equals 3, what I'm going to do is measure my training error only on the 3 examples that I've actually fit my hypothesis to, and not on all the other examples that I had deliberately omitted from the training process. So just to summarize, what we've seen is that if the training set size is small, then the training error is going to be small as well. Because if you have a small training set, it's going to be very easy to fit your training set very well, maybe even perfectly. Now, say I have m equals 4 examples. Well then, a quadratic function can no longer fit this data set perfectly. And if I have m equals 5, then maybe a quadratic function can fit this data so-so, but as my training set gets larger, it becomes harder and harder to ensure that I can find a quadratic function that passes through all my examples perfectly. So in fact, as the training set size grows, what you find is that my average training error actually increases. And so if you plot this figure, what you find is that the training set error, that is the average error on your hypothesis, grows as m grows. And just to repeat, the intuition is that when m is small, when you have very few training examples, it's pretty easy to fit every single one of your training examples perfectly, and so your error is going to be small. Whereas when m is larger, then it gets somewhat harder to fit all of your training examples perfectly, and so your training set error becomes a little bit larger. Now, how about the cross-validation error? Well, the cross-validation error is my error on this cross-validation set that I haven't seen. And so, when I have a very small training set, I'm not going to generalize well. I'm just not going to do well on that. So, right, this hypothesis here doesn't look like such a good one. And it's only when I get to a larger training set that, I'm starting to get hypotheses that maybe fit the data somewhat better. So, your cross-validation error and your test set error will tend to decrease as your training set size increases, because the more data you have, the better you do at generalizing to new examples, or just the more data you have, the better the hypothesis you fit. So if you plot JTrain and JCV, this is the sort of figure you get. Now let's look at what the learning curves may look like if we have either high bias or high variance problems. Suppose your hypothesis has high bias, and to explain this I'm going to use our standard example of fitting a straight line to data that can't really be fit well by a straight line. So we end up with a hypothesis that maybe looks like that. Now let's think what would happen if we were to increase the training set size. So if instead of 5 examples like what's drawn there, imagine that we have a lot more training examples. Well, what happens? If you fit a straight line to this, what you find is that you end up with pretty much the same straight line. I mean, a straight line just can't fit this data, and getting a ton more data, well, the straight line isn't going to change that much. This is the best possible straight line fit to this data, but the straight line just can't fit this data set that well. So if you plot the cross-validation error, this is what it'll look like. Up here on the left, if you have a really minuscule training set size, like you have maybe just 1 training example, it's not going to do well. But by the time you've reached a certain number of training examples, you've almost fit the best possible straight line, and even if you end up with a much larger training set size with much larger value of m, you're basically getting the same straight line. And so the cross-validation error, let me label that, or test set error, will plateau out or flatten out pretty soon once you've reached beyond a certain number of training examples that lets you pretty much fit the best possible straight line. And how about training error? Well, the training error will again be small, and what you find in a high bias case is that the training error will end up close to the cross-validation error. Because you have so few parameters and so much data, at least when m is large, the performance on the training set and on the cross-validation set would be very similar. And so this is what your learning curves will look like for if you have an algorithm that has high bias. And finally, the problem of high bias is reflected in the fact that both the cross-validation error and the training error are high, and so you end up with a relatively high value of both JCV and JTrain. This also implies something very interesting, which is that if a learning algorithm has high bias, as we get more and more training examples, that is, as we move to the right of this figure, we'll notice that the cross-validation error isn't going down much. It's basically flattened out. And so if a learning algorithm is already suffering from high bias, getting more training data by itself will actually not help that much. And as a concrete example, in the figure on the right, here we had only 5 training examples and we fit a certain straight line, and when we had a ton more training data, we still ended up with roughly the same straight line. And so if a learning algorithm has high bias, just getting a lot more training data, that doesn't actually help you get a much lower cross-validation error or test set error. So knowing if your learning algorithm is suffering from high bias seems like a useful thing to know, because this can prevent you from wasting a lot of time collecting more training data where it might just not end up being helpful. Next, let's look at a setting of a learning algorithm that may have high variance. Let's first look at the training error. If you have a very small training set, like 5 training examples shown on the figure on the right, and if we're fitting, say, a very high order polynomial, I've written a 100th degree polynomial, which really no one uses, but just for illustration. And if we're using a fairly small value of lambda, maybe not 0, but a fairly small value of lambda, then we'll end up fitting this data very well, but with a function that overfits this. So if the training set size is small, our training error, that is JTrain of theta, will be small. And as this training set size increases a bit, we may still be overfitting this data a little bit, but it also becomes slightly harder to fit this data set perfectly. And so as the training set size increases, we'll find that JTrain increases, because it's just a little harder to fit the training set perfectly when we have more examples, but the training set error will still be pretty low. Now, how about the cross-validation error? Well, in the high variance setting, our hypothesis is overfitting, and so the cross-validation error will remain high even as we get, a moderate number of training examples. And so maybe the cross-validation error may look like that. And the indicative diagnostic that we have a high variance problem is the fact that there's this large gap between the training error and the cross-validation error. And looking at this figure, if we think about adding more training data, that is taking this figure and extrapolating to the right, we can kind of tell that, you know, the two curves, the blue curve and the magenta curve, are converging to each other. And so if we were to extrapolate this figure to the right, then it seems likely that the training error would keep on going up and the cross-validation error would keep on going down. And the thing we really care about is the cross-validation error or the test set error, right? And so in this sort of figure, we can kind of tell that, you know, if we keep on adding training examples and extrapolate to the right, well, our cross-validation error will keep on coming down. And so in a high variance setting, getting more training data is indeed likely to help. And so this again seems like a useful thing to know if your learning algorithm is suffering from a high variance problem, because that tells you, for example, that it may be worth your while to see if you can go and get some more training data. Now, on the previous slide and this slide, I've drawn fairly clean, fairly idealized curves. If you plot these curves for an actual learning algorithm, sometimes you will actually see, you know, pretty much curves like what I've drawn here, although sometimes you see curves that are a little bit noisier, a little bit messier than this. But plotting learning curves like these can often help you figure out if your learning algorithm is suffering from bias or variance, or even a little bit of both. So when I'm trying to improve the performance of a learning algorithm, one thing that I'll almost always do is plot these learning curves. And usually this will give you a better sense of whether it's a bias or variance problem. And in the next video, we'll see how this can help suggest specific actions to take or to not take in order to try to improve the performance of your learning algorithm. We've talked about how to evaluate learning algorithms, talked about model selection, talked a lot about bias and variance. So how does this help us figure out what are potentially fruitful or potentially not fruitful things to try to do to improve the performance of our learning algorithm? Let's go back to our original motivating example and go figure this out. So here is our earlier example of maybe having fit regularized linear regression and finding that it doesn't work as well as we're hoping. We said that we had this menu of options. So is there some way to figure out which of these might be fruitful options? The first thing on our list was getting more training examples. And what this is good for is this helps to fix high variance. And concretely, if you instead have a high bias problem and don't have any variance problem, then we saw in the previous video that getting more training examples, well, maybe just isn't going to help much at all. So the first option is useful only if you, say, plot the learning curves and figure out that you have at least a bit of a variance, meaning that if the cross-validation error is, you know, quite a bit bigger than your training set error. How about trying a smaller set of features? Well, trying a smaller set of features, that's again something that fixes high variance. And in other words, if you figure out by looking at learning curves or something else that you instead have a high bias problem, then for goodness sakes, don't waste your time trying to carefully select out a smaller set of features to use, because if you have a high bias problem, using fewer features is not going to help. Whereas in contrast, if you look at the learning curves or something else and figure out that you have a high variance problem, then indeed trying to select out a smaller set of features that might indeed be a very good use of your time. How about trying to get additional features? So adding features, usually, not always, but usually we think of this as a solution for fixing high bias problems. So that if you're adding extra features, is usually because your current hypothesis is too simple, and so we want to try to get additional features to make our hypothesis better able to fit the training set. And similarly, adding polynomial features. This is another way of adding features, and so that's another way to try to fix a high bias problem. And if your learning curves show you that you instead have a high variance problem, then again, this is maybe a less good use of your time. And finally, decreasing and increasing lambda. These are quick and easy to try. I guess these are less likely to be a waste of many months of your life, but decreasing lambda, you already know, fixes high bias. In case this isn't clear to you, do encourage you to pause the video and think through this. that convince yourself that decreasing lambda helps fix high bias, whereas increasing lambda fixes high variance. And if you aren't sure why this is the case, do pause the video and make sure you can convince yourself that this is the case, or take a look at the curves that we were plotting at the end of the previous video and try to make sure you understand why these are the case. Finally, let's take everything we've learned and relate it back to neural networks. And here I just want to give some practical advice for how I usually choose the architecture or the connectivity pattern of the neural networks I use. So if you're fitting a neural network, one option would be to fit, say, a pretty small neural network with, relatively few hidden units, maybe just one hidden unit. If you're fitting a neural network, one option would be to fit a relatively small neural network with, say, relatively few, maybe only one hidden layer and maybe only a relatively few number of hidden units. So a network like this might have relatively few parameters and be more prone to underfitting. The main advantage of these small neural networks is that they're computationally cheaper. An alternative would be to fit a maybe relatively large neural network with either more hidden units, so if there's a lot of hidden units in one layer, or with more hidden layers. And so these neural networks tend to have more parameters and therefore be more prone to overfitting. One disadvantage, often not a major one, but something to think about, is that if you have a large number of neurons in a neural network, then it can be more computationally expensive. Although within reason, this is often, hopefully, not a huge problem. The main potential problem of these much larger neural networks is that they could be more prone to overfitting. And it turns out that if you're applying a neural network, very often using a larger neural network, often it's actually the larger the better, but if it's overfitting, you can then use regularization to address overfitting. And usually using a larger neural network but using regularization to address overfitting, that's often more effective than using a smaller neural network. And the main possible disadvantage is that it can be more computationally expensive. And finally, one of the other decisions is, say, the number of hidden layers you want to have, right? So do you want one hidden layer, or do you want 3 hidden layers as I've shown here, or do you want 2 hidden layers? And usually, as I think I said in the previous video, using a single hidden layer is a reasonable default. But if you want to choose the number of hidden layers, one other thing you can try is find yourself a training, cross-validation, and test set split, and try training neural networks with 1 hidden layer, with 2 hidden layers, with 3 hidden layers, and see which of those neural networks performs best on the cross-validation set. So you take your 3 neural networks with 1, 2, and 3 hidden layers, and compute the cross-validation error J, CV on all of them, and use that to select which of these is, you think, the best neural network. So that's it for bias, variance, and ways like learning curves to try to diagnose these problems, as well as what these things imply for what might be fruitful or not fruitful things to try to improve the performance of a learning algorithm. If you understood the contents of the last few videos, and if you apply them, you'll actually be much more effective already at getting learning algorithms to work on problems than even a large fraction, maybe the majority of practitioners of machine learning here in Silicon Valley today doing these things as their full-time jobs. So I hope that these pieces of advice on bias, variance, learning curves, and diagnostics will help you to much more effectively and powerfully apply learning algorithms and get them to work really well.